Instrumentation is an important part of the electrodiagnostic study. An operator who is familiar with the instrument settings can navigate through the test procedures quite easily. This not only reduces the time of the EDX study, but also reduces the patient discomfort. When unexpected results or waveforms occur, the user can quickly examine if that represents a real abnormality or an artifact. As new methods of recordings and analysis are developed, the operator familiar with instrumentation can implement those techniques in his or her practice. The EDX instrument has evolved over the last 7 decades. In the early 50s, the EDX system was used mostly for needle EMG. In this system from 1953, we find an oscilloscope to display signals, a speaker to listen to their sound, and a tape recorder to make an analog copy of the potentials. There is no stimulator. When the usefulness of nerve conduction studies was demonstrated, the electrical stimulator became an essential component of the system. Here is a system from 1960s with a black stimulator handle that was used until just 10 years ago. When storage oscilloscopes became available, one could freeze the EMG waveforms. Polaroid cameras were used to obtain a hard copy of the waveforms. Here is one such recording in the repetitive nerve stimulation test performed in 1965. The amplitude decrease is seen quite easily. Here is a recording of the compound muscle action potential on the top trace and a sensory nerve action potential on the bottom trace. In the late 70s and mid-80s, the instruments started getting digital. The ability to save signals in a digital format opened new ways of analysis. Algorithms were developed to make automatic measurements of the potentials. The trend continued in the 90s as more powerful algorithms were introduced for jitter measurement in single fiber EMG or to identify motor net potentials using techniques like multi-motor net analysis. Today, the electrodiagnostic system also performs other tasks such as generate a report, communicate with electronic medical records and hospital information systems, and so on. Many systems can be networked to create a central database for measurements. One can also review the studies remotely. Systems are available from many different vendors with different functionality, shapes, and capabilities. Nevertheless, all of them have one common objective: to record and amplify a very low voltage electrophysiologic potential in the presence of high voltage noise. The recording conditions can be quite extreme, where the noise voltage may be 100 or even 1,000 times bigger than the neurophysiologic signal voltage. In brief, the neurophysiologic potential is recorded by electrodes. Those voltages are relayed to the amplifier via leads and cables. The ambient noise and interference is also registered by the electrodes and their leads. The amplifier magnifies the neurophysiologic signal while attenuating the background noise. This is further aided by so-called filters. The amplified signal is digitized using the analog to digital converter. The digitized signal is processed using digital signal processing algorithms. This can include techniques such as filtering, smoothing, averaging, etc. The signals are then displayed on the computer terminal along with any measurements that may be made. A speaker is also used to listen to the signals. In this presentation, our goal is to discuss the role of these components to obtain high-quality recordings. We will also discuss how the signals may be affected when the settings of these components are altered. Finally, we will discuss strategies to attenuate noise and artifacts.